Okay, in the last video, we talked about wrapper methods that are model specific. Basically, if you see the slide, you generate a particular subset, you have fixed a particular machine learning model, and that model actually guides you to select a particular subset based on the holdout set. If you have a training data, you've partitioned the training data into holdout set and the training data for this particular task. Then the wrapper methods, they actually utilizes the actual model to guide the search for a best subset. But the problem for wrapper methods, as we saw in the previous video, was it is time expensive. It needs a lot of trainings for different subsets. Later on, we will see the total number of subsets. They are basically 2 raised power d, which is a huge thing. So if we go for all the subsets, we have to, if not for all, even if for a few subsets, we have to retrain. The training itself is expensive. And if we have to retrain again and again, it is really a time expensive task. In embedded methods, again, we have some ML method, ML model. We have to fix the ML model just like the wrapper methods. But magically, something happens is we throw all the data, all the features, rather than a subset. See, in the previous methods, both in filter and in wrapper, we have a subset generator which generates a subset. But in embedded methods, there is no subset generator. We actually set all the data. We actually throw all the data in. And let's say it's a supervised task, so we set the label as well. We throw all the data, and there is some machine learning model, maybe SVM or neural network or random forest or some model. We train that model just once, not again and again. And the output of the model, it actually weights different features. It weights different features in a way that some of the features, they are important, and the other features, they are less important. So that's really fast, really powerful, model specific. And so model specificity indicates that how will it perform in the real scenario based on this particular model, because we are fixing the model. And we saw that filter methods were fast because they do not require model specificity, but then the filter methods, they suffer from the true indication of how will they perform on a particular model when the model dives in. So this embedded method, it has the beauties of both filters and wrappers. So filter method is fast, so does the embedded method, because it requires training just once. Wrapper method was model specific, so does the embedded method. Embedded method is also model specific. So it is fast as well as model specific. So but how this magic is done? I mean, how these features are selected. Let me give you an example. Let me give you an example with linear regression based on L1 regularization, sometimes called the LASSO regression. Let me give you an example. Let's say yi is w naught plus w1 x1i plus x2i plus dot dot dot. Sorry, that is w2 here. Yeah. So wd x di. So let's say that's your regression model. And what you do really is you set a cost function, which is rather than writing this as equal, you just set that thing as and rather than this equal, you say, okay, minus this and minus this, that should be 0. Or if that is 0, then its square should be 0. And you really want these weights to minimize this number. Ideally, you want this number to be 0. But then to avoid overfitting, what you do is you really apply this L1 regularization, sometimes called the L1 regularization, which is the the sum of the absolute values. Here, W is a vector of W0, W1, dot, dot, WD. That's a vector. And your goal is to minimize all that, find out the W that minimize this data term and this regularization term. Obviously, there is a lambda parameter called regularization parameter, but I'm not going into that detail. I'm just want to focus that this L1 regularization, what it will do is some of the weights, they will be really high. So maybe W1 is a high, W3 is high, W7 is high, but several weights, they will be really small or exactly zero, which means the weights that are really small or exactly zero, the features corresponding to those are unimportant because they are they're not contributing towards the regression here. So that is just one-time training along with this L1 regularization. Um, and after that training, you'll be having certain weights, and different weights, they will signify the importance of different features. So one-time training, the weights, different weights, the values or the magnitudes of the weights, they are basically the importance of the features, and you can select the best subset based on the weight values. Yeah, so that is embedded method, and it's really powerful method. A lot of machine learning models, they actually are embedded. They fall under these embedded methods. So almost all regularization methods, neural networks, decision tree based methods, and I mean several. So we can select features using these embedded methods as long as the one-time training of the model is one-time training of the model is affordable. Obviously, that is much better than wrapper method in a case where we may have to retrain again and again and choose the subsets. But on the other hand, these embedded methods, they are very, very, very specific to the model, which is also the case in wrapper methods as well. But in wrapper methods, we can somehow use a particular machine learning model as a black box, and we can select the features that are less specific, although they are specific to the model, but they might be assumed to be comparison to embedded method, they are less specific to the model. In case of embedded methods, they are highly specific to the model, and using these features, selected features other than this particular model, may be a disaster. So that's a brush up of the models, the methods, feature selection methods, filter, wrapper, and embedded. Let me just summarize. Filter uses a criteria independent of a machine learning model. Wrapper uses a machine learning model, but it may requires a lot of retrainings. Embedded again uses a machine learning model but trains only once and learn weights, and these weights, they signify the importance of different features, and based on those weights you can select a subset of features. So from the next video onwards, we will be talking about the search strategy and the subset generation process and all that stuff. um, I'm deliberately delaying the implementation of these methods in Python because I need to cover a lot of bits and bytes and gaps that are there inside so far. I need to cover those before going towards the Python implementation. So don't worry if you are thinking that why we are not going to Jupyter and why not we implementing these things. We will implement each and every method. I will show you the implementation in live, each and every method. But hold on for just a few more videos to just learn more about the implementation and details about these methods, and then we'll be having a better way of implementing those and better understanding of the implementations and the results from there. So hope to see you in the next video. Last but not the least, I should also mention the embedded method, which means what if we really use the training just once, and we just select our features based on different weights and stuff like so. So for that, for embedded methods, sklearn or scikit-learn provides us a model that's select from model based on feature values. So from sklearn, So first let me give a heading that we are going to use embedded method or just embedded. Okay, so embedded. So from scikit-learn dot feature selection, from scikit-learn feature selection, import select from model. Yeah, so that is needed. Let's say our model is let's say is linear sport vector machines that we're going to use with L1 regularization. So let's copy that. Let's so remember in my previous videos, I talk about L1 regularizer. So let's say that. Let's say we have M is equal to linear SVC with overfitting controller as 0.01. That's a parameter that controls the overfitting. If you really want to know much more about this parameter and much more about this SVM, we have a full-fledged course on SVM. Just on SVM, we have a full course on that, which explains all these terms in a big detail. Penalty or the regularization is, let's say, L1. And do we really want to go to a dual space? Because this SVM, it has a Lagrange, its formulation has a Lagrangian dual, and there we solve it. So whether we are going to make it dual or not, it depends completely. So here we are not saying that go to dual space and solve it. Yeah, so fit X and Y. Remember, we are fitting X, not X new. So and really I want to show you the power and the efficiency of this model. Fitting this X basically, we are fitting 6,004 data points, each with dimensions 2,401 with linear SVM. And this is just one-time training. So all I want to show you that if it, oh, that's a problem. What's the problem? Penalty, I guess I have wrong spelling of penalty, P-N-A-L-T-Y. Yeah. All I want to show you that one-time training is not that hard for the data set with high dimensions. Although in some cases it is, but we will see, yeah, it returns. It returns very quickly because it is just one-time training. Think about the same with wrapper method. If we just replace logistic regression with linear SVM and we apply recursive feature elimination, then don't expect this s.fit to return quickly. Although you have seen that linear SVM returns very quickly even on very high dimensional data. But this wrapper method requires a lot of retrainings, training again and again and again several times, and this makes this slower. So embedded, we have trained just once. Now this L1 regularizer, actually it assigns weights to different features, and based on the weights, we are going to select the best features. So T is select from model. Model is M, prefit, that's a parameter. Let's make it true. So that is our T. Yeah, so T is available. If you see the parameters of T, that is select from model, the linear, the model inside that is embedded inside is this one, and the max number of features we have not set anything. It will select on its own based on the default thresholds. So yeah, so here what we do is X new 2 is T dot transform X, and if you see the shape of X new 2 dot shape, that is basically 257. So what happens is this L1 regularizer on linear SVM, that embedded method basically give good weights to just 257 features out of 2,401 features. and the data is transformed to that, and the dimensionality has been reduced. Now, if we want to reduce the dimensionality of any test data that is coming, we can just call this t.transform function and we are good to go. After reducing this dimensionality, we can use this xnew2 for training a linear SVC model. Remember this embedded method is very strongly tied up to the model and the penalties you have used. So if you have selected the features using embedded method and with a particular model like SVM here, and you used a different model for training after selecting through another different model, that may cause serious problems. So yeah, embedded method is really fast. It requires one-time training, and this is not just linear SVM that fall under this. Actually, neural networks fall under this. Decision tree based methods, ensemble methods, random forest, different methods, they fall under this. I have just shown you one example. There are others as well. So this is embedded is fast, model guided. It is guided by model. Wrapper method is slow. It is also guided by model. Filter method is really fast, has no machine learning model at the end. But at the end of the day, which one works better completely depends upon the data and the task at hand. Remember, in machine learning and data science, nothing is absolutely correct without seeing the data. This is the data that actually guides, and data and the particular task you're going to perform on the data, that actually guides which method will work on this particular data. So I'm not saying anything about the betterment of embedded method over wrapper method, or the betterment of wrapper method over filter method. I cannot say anything without seeing the data. Maybe on different data set, a different kind of settings work better than. So it varies from data to data and task to task. So normally what happens in practice is filter methods normally are used to filter out as a pre-processing step. And after reducing a good amount of dimensions using filter methods, people go to embedded or wrapper methods to further reduce the dimensionality of the data. And that dimensionality is model guided and somehow give a better indicator of the generalization when the model eventually will be deployed. So yeah, so that's the brush up of embedded methods, wrapper methods, and filter methods.